Hello and welcome to an overview of Data Acquisition Systems. I'm Andy Taer, Business Development Manager for ESC Spectrum. Welcome to this presentation of an overview of data acquisition systems for continuous emissions monitoring. We'd like to thank the 7F Users Group and Combined Cycle Journal for inviting us to participate in this digital conference. And before we get underway, I want to introduce you to ESC Spectrum Systems. Our StackVision and Prism DAS products are the market leaders in helping industrial and utility plants comply with air quality regulations that require continuous monitoring. We also offer comprehensive CEMS services, including new CEMS systems, maintenance contracts, repairs, training, and stack testing. So with that introduction, let's now jump right into the presentation. Let's start with the acronyms. Whether you refer to a DAS as a data acquisition system or data acquisition and handling system, we're talking about the same thing. The primary functions of a DAS are to monitor the air emissions data from a plant's continuous emissions monitoring system, or CEMS, perform the calculations necessary for regulatory reporting, manage alarms that alert environmental and operations staff about potential emissions exceedances or operational issues, maintain a secure database of historical records, and automate regulatory reporting. There are a number of regulatory programs that require a DAS for CEMS monitoring and reporting, and depending on your industry, you may need to comply with one or more of them. Now let's look at the primary functions of a DAS. First, a DAS collects air emissions data. This data primarily comes from analyzers that measure the concentration of contaminants in air emissions that are continuously sampled from sources at a plant. Second, it collects quality assurance records. These records are used to measure the validity and accuracy of the data collected. Third, the DAS flags data to indicate whether it's valid and in control based on regulatory requirements. Fourth, it performs calculations including generation of the required averaging intervals and some reporting parameters. And fifth, the DAS performs data substitution. This involves substitution of computer-generated values for periods where there is no valid CEMS data available. Sixth, the DAS produces data reports required by regulatory agencies, including the EPA and the states. And lastly, the DAS creates and maintains an auditable record of emissions data. Regulations require that an auditable record be maintained, typically for 3 to 5 years. So now let's take a look at the components of a typical CEMS DAS system. Here we have a sketch of a simple CEMS system, and let's take a walk through the components. On the left side, we have the CEMS sampling and analysis system. And in this example, we have a probe near the top of the stack that draws the air sample into the system. From there, the sample travels down through an umbilical to a sample conditioner where moisture is removed. The dry air sample then enters the analyzers where the concentrations of contaminants are measured. For gas turbine electric power plants, that typically includes nitrous oxides and carbon dioxide. And depending on the analyzer, measurements can be read using analog or digital communications such as Modbus. Now let's move to the DAS components on the right side and start with the data controller, which is the front-end device for the DAS. It's typically located in the CEMS shelter where it receives data directly from the analyzers. The controller performs a number of functions that I'll elaborate on shortly, then passes the data via the plant network to the DAS server where the core DAS software application runs. A robust DAS will run on a true server class computer that can be a physical or virtual server and will use a SQL Server database. Users are able to access the DAS data and perform reporting functions from workstations on the DAS network. Now let's talk about the functions performed by the data controller. The controller translates the analyzer signals into concentration values, typically parts per million or ppm. It then constructs the averaging intervals required under a plant's air permit, typically 15-minute, 1 hour, and so on, and these may be block or rolling averages. The controller validates the data as good or bad. Only good data can be used for regulatory reporting. Bad data can result from failed calibrations, downtime, and insufficient amount of data within a required interval of time, to name a few. The controller can store up to 1 year of data and provides redundancy to the DAS server. It initiates the daily QA calibrations, which involves running through the required calibration sequences and storing the resulting data. The controller assigns flags to the data to mark it as in calibration, in maintenance, startup, shutdown, and so on. The flags are used to automate the identification of data as valid or invalid. The controller triggers alarms that provide alerts to emissions exceedances and operational conditions. And finally, the controller continuously transfers the data to the DAS server via the plant's network. Now let's take a look at the key functional areas of a DAS. There are 7 key functional areas that every DAS should have, and let's walk through each one, starting with parameter relationships and calculations. Your DAS should include a graphical display of the CEMS parameter relationships and the equations used for their calculation. Here's an example from StackVision's CEMScape that shows a graphical model of all of the parameters in our example CEMS system. Your DAS should allow you to select any parameter in your system and see what parameters are used in its calculation. Let's now look at an example of how any parameter here can be selected and extracted into its own view so that its relationships become clear. So here we've selected NOx pounds per hour and extracted it and its related parameters into their own view. On the left side, we can see the equation used to calculate the NOx pounds per hour value. Looking at the equation, note that it's dependent on the O2, NOx ppm, and flow gas parameters, and looking at the graphic display, you can see the dependency lines feeding into it from these parameters. Similarly, in the bottom example, we've highlighted the NOx pounds per million BTU parameter, and we can see its equation and the parameters that feed into its calculation. This feature is very useful for understanding your DAS, troubleshooting data issues, and helps when adding new monitoring parameters to the DAS. Now let's move on to data management, and to illustrate this function, we'll look at examples from StackVision's Data Lab. Your DAS should allow you to view and manage your data by selecting one or more parameters, the date range, and interval. You should be able to see data flags, recent inaction codes, excess emissions, and many other important pieces of information. Let's take a quick look at how you can view different time intervals. So in this example, we started with the 1 hour interval and are able to select any hour and then drill down and view the underlying 1 minute data. This is an important function that should allow you to view all of the averaging intervals that are set up in your DAS. Moving on, let's take a look at data validity and flagging. Regulatory agencies only allow you to report data that is valid. So let's take a look at what that means and show an example from StackVision. One of the more common approaches for determining data validity requires you to record at least 1 valid minute of data in each quarter hour. All valid minutes in the quarter hour are then averaged to make a valid quarter, and 4 valid quarterly averages are then used to construct a valid hour. Different rules apply when your system is in calibration, so let's take a look at an example. In order for the hour during which calibration occurs to be valid, you must first complete and pass the calibration, and second, record 2 good minutes separated by at least 15 minutes. So on the left side, the hour was valid because following successful completion of the calibration, we were able to get a good minute in the 3rd quadrant and in the 4th quadrant, separated by 15 minutes. Using StackVision's Data Lab, here's an example of what that might look like in your DAS. In Data Lab, the C flag means the analyzer was in calibration, and the less than symbol means the interval was not valid. Here we can see that the calibration started at the start of hour 6 and ended at 6:15. Moving to the 15-minute interval, we can see again that the 6 to 6:15 interval was in calibration and therefore not valid. but we can also see that we have valid readings during the subsequent quadrants of the hour. Accordingly, when we look at the 1 hour interval data, we can see that it's flagged as in calibration, but valid as denoted by the greater than symbol. The greater than symbol means that although some data was missing during the hour, it met the requirements for building a valid data average for that hour. Now let's take a look at calibration checks. Part 75 requires that you run daily calibrations on all operating days and within 26 hours after the last successful online calibration and within 8 hours of startup. Your DAS should be capable of automating your daily calibrations and should allow you to manage daily calibration checks, change data such as the reference values and actual values, and reevaluate calibration errors. In StackVision, CalLab provides this functionality and manages 7-day calibration error tests, offline calibration demonstrations, and cycle/response time tests. Your DAS should allow you to see the current calibration status of each parameter. It should automatically calculate calibration errors as data changes, and it should allow you to export data directly to Excel. Now let's move on to notifications and alarms. Your DAS should have an alarm and notification function, and alarms should be generated whenever an exception event occurs. Alarms should cover data, system, and application exception events. A data alarm example would be anything that may impact compliance, such as excess emissions or failed calibrations. System alarms would be anything that may impede your DAS operations, such as network communication errors or low disk space. And processing errors in your DAS would be an example of an application alarm. Your DAS should display all of the active alarms and the alarm history. And the alarms function should require users to acknowledge their awareness of existing alarms and specify a reason for an alarm and a corresponding action code that notes what was done about it. These steps categorize potential events necessary for required performance summary reporting. Now we'll shift our focus to reporting, the final key functional area of a DAS. Although presented last, reporting is one of the most important features. Your DAS should include a large library of reports for regulatory, QA certification, system design, and general reporting. As an example, StackVision comes standard with over 90 reports and allows further customization when needed. And here are just some quick examples of common reports. A downtime report showing the start and end times, duration, and reason and action codes. An exceedance report showing similar information as the downtime report. And performance summary that summarizes the excess emissions and the CEMS downtime. And very importantly, you should be able to easily generate the Part 75 EDR or electronic data record. StackVision has an easy-to-use wizard that walks you through generation of the EDR in the required XML format. Now that we've covered the DAS, we'll close with a few Part 75 audit preparation tips. It's important to always be prepared because audits are not always announced ahead of time. The first thing you should do is download EPA's Part 75 CEM Field Audit Manual. This manual is used as a guide by EPA's field auditors, so it'll give you valuable insight into what they'll be looking for if they should audit your facility. You should train your staff on all aspects of your CEMS and DAS so that deviations, excess emissions, and downtime events are minimized and proper documentation is maintained in your DAS. You should run through self-audits to identify weaknesses and deficiencies. You should review all of your air compliance permits and know their specific requirements line by line. And for Part 75, the single most important document is your QA/QC plan. The auditor will use it to judge the performance of your plant, so make sure it's up to date and correctly implemented. In your DAS, you should review the data for excess emissions, downtime, and QA activities. Make sure there are no data gaps and that exceptions are well documented. So to conclude, with preparation, training, self-auditing, and thorough knowledge of your permits, you'll be ready when the auditor calls. And thank you for attending this presentation.